pleasure to announce what is the Bergweiler stock on the boundary of an immediate attracting basin of a hyperbolic entire function.
Thank you very much. So, well, first I would like to thank the organizers. Well, thanking them for organizing an excellent conference. Well, at least excellent so far. I hope this talk is not going to change it. And of course, I also like to thank the organizers for inviting me. Well, and not only the scientific program has been excellent, also the trip yesterday afternoon, the barbecue and bonfire, but well, nevertheless, we have to return to work and mathematics somehow. And I apologize, I do not have chocolate, but so let us start. So I will be talking about some joint work with Jie Ding, who is also at this conference. And well, the work will be on, you have seen and heard the title already, on immediate attracting basins of entire functions. So what is the setup? So we consider an entire function and the attracting periodic point of some period P. So, well, what is periodic point? It means that Fp of Z naught is Z naught, so Fp, of course, is a piece iterate, and the derivative of Fp at this point, Z naught, is less than 1. And when I talk about period, I also always mean minimal period. So it means P is the smallest number such that Fp of Z naught is Z naught. So Fk of Z naught is different from Z naught if K is less than P. So if you have such an attracting periodic point, then in a neighborhood of Z naught, the iterates of Fp will converge to Z naught. And by A, Z naught F, we denote the attracting basin. So this is a set of all points for which the iterates of Fp converge to Z naught. Well, it is well known and easy to prove that this attracting basin is in the f of f. So this is a Fatou set. And so the attracting basin is in the Fatou set. The boundary of the attracting basin is in the Julia set. I suppose at this conference I do not have to define what the Fatou set and the Julia set are. And well, besides the Fatou set and the Julia set, we will consider one further set. This is the escaping set. This consists of the points which tend to infinity under iteration. Well, then I said already the attracting basin is contained in the Fatou set, and it contains the point Z naught. So the component of the attracting basin which contains the point Z naught, this we call the immediate attracting basin, and the notation is A star of Z naught of F. So this is then a component of the Fatou set. So let us first consider these attracting basin and immediate attracting basins for the exponential function, or more generally for the functions E lambda of Z, which are lambda e to the Z. So first, let's note that if E lambda has an attracting fixed point, then the Fatou set is actually connected. So if E lambda has an attracting fixed point, well, then the Fatou set is equal to the attracting basin of this fixed point. And because this attracting basin is connected, the attracting basin is equal to the immediate attracting basin. So we will be interested in later in the boundary of the immediate attracting basin. So our main interest is in the case where you have periodic points of period greater than 1. But to start, we consider the case where the period is 1, so where we have a fixed point. And in this case, the boundary of the attracting basin is, well, the boundary of the Fatou set, which is the Julia set. And we are interested in the dimension of these boundaries of the immediate attracting basins. So in this case here, this is the Julia set, and there is a old result by McMullen, which says that for these functions lambda e to the z, so the dimension of the Julia set is equal to 2, and actually he proved this by showing that the dimension of the escaping set is 2, and showing that the escaping set is contained in the Julia set for these functions. So here we have that, well, and I should say, when I say dimension, I always mean Hausdorff dimension. And again, I think Julia set and Hausdorff dimension, maybe at this conference, I don't have to go through the definitions. So, but if you take this result of McMullen together with the result that the immediate basin of attraction is a Fatou set and its boundary is a Julia set, so what you get is, if E lambda has an attracting fixed point, then the boundary of the immediate basin of attraction of this fixed point has Hausdorff dimension 2. So this is simply because this boundary is equal to the Julia set, which by the result of McMullen has dimension 2. So our starting point was a result by Preslav Baransky, Boguslav Karpinska, and Anna Stunek, who showed that this changes if you go to periodic points of period greater than 1. So they showed that if you have an attracting periodic point of period greater than 1, then the boundary of the immediate basin has Hausdorff dimension strictly less than 2. They also showed that the Hausdorff dimension is strictly greater than 1. But in this talk, we will be concerned with upper bounds. So I only stated the upper bound here. So here are some pictures. So there is an attracting periodic point of period Z0. Well, on the left is a fixed, Z0 is a fixed point. In the middle, it has period 2. On the right, it has period 3. And so, and if you look at the yellow region, which contains Z0, then the result is, in the left picture, it has dimension 2, and in the middle and the right, it has dimension strictly less than 2 by the result. So the next result of relevance here is by Mariusz Urbanski and Anna Stunek. They proved if E lambda has an attracting periodic point, then the dimension of Julia set minus escaping set has a dimension strictly less than 2. So the non-escaping points in the Julia set have dimension strictly less than 2. So what this means, so when you consider the boundary of the immediate attracting basin, well, and want to prove that the dimension is less than 2, you only have to consider the escaping. So Krzysztof, Bogusia, and Anna, so in order to prove that the dimension of the boundary of the immediate attracting basin is less than 2, so they only had to consider the dimension of the intersection of this boundary with the escaping set. So, and they proved that this intersection actually has dimension 1. 1 is less than 2, so this combined with the result by Mario Sherbansky and Anna Sunik then gives the result that the immediate basin, the boundary of the immediate basin has a dimension strictly less than 2. Well, and what I want to discuss in this talk is an extension of this to more general functions. So not only the functions lambda e to the z, but also more general functions. And I should say here, when I say extend this result, so I mean the second result. I would have liked to talk also about extension of the first result here, but so far we do not have anything where I could talk about. So I will talk about extension of this second result. So when you want to extend results for exponential functions to more general entire functions, a very natural class to look at is a so-called Speiser class. So this is a class of functions usually denoted by S after Speiser, so for which the set of singularities of the inverse is finite. The set of singularities here I denoted by sing of F inverse. This actually appeared in several other talks already. However, every author seems to have his own notation for this set. So it appeared with the notations S of F or SV of F or sing of F. So, well, anyway, at least I know that there were 3 talks where it appeared and all had different notation, and my notation is also different from all previous notations. So what is this? It consists of the critical and asymptotic values, as was mentioned already. So what is a critical value? Critical value is a value W naught, such that there is a point Z naught called critical point. So where F prime of Z naught is 0 and F of Z naught is W. So the prototype is a function z squared with z naught equal to w naught equal to 0. So z squared has a 0 at the origin, so f of 0 is 0. And so this is a critical value. And indeed, if you take the inverse of z squared, this is a square root, it does have a singularity at 0. So the other type of singularity is the asymptotic value. This is here you have a curve going to infinity, and f of z tends to a value w naught as z tends to infinity along this curve. So the prototype is the exponential function here again. If your curve is a negative real axis, and so if you go to minus infinity, so if you go to minus infinity along the real negative axis, well, then the exponential function tends to 0. So 0 is an asymptotic value, and indeed 0 is singularity of the logarithm, which is the inverse of the exponential function. So let's consider examples. The exponential function, or more generally, the function lambda e to the z, I mentioned already. So 0 is an asymptotic value. It is not difficult to say that there are no other asymptotic values. Then there are also no critical values, because the derivative is again the exponential function, which has no zeros. So the exponential function has only one, there the inverse has only one singularity. So another example, say, is cosine. So the derivative is, well, first you can convince yourself cosine has no asymptotic values. So, and if you look at critical values, the derivative is minus sine, and whenever the sine is 0, the cosine is plus or minus 1. So here you have 2 singularities of the inverse. And another example is the sort of error function, integral from 0 to z e to the minus t squared dt. Well, first, again, this has no critical values because the derivative is exponential of something, so the derivative has no zeros, but it has asymptotic values. If you go to the positive real axis, it stands to root pi over 2, and if you go to infinity along the negative real axis, it is minus 1/2 root pi. So you have two singularities of the inverse, plus minus 1/2 root pi. Well, let me make a general remark here. So if you have an entire function where the inverse has only where the inverse has only one singularity, then your function is, well, and normalize the thing so that the singularity of the inverse is at 0, then your function is the exponential function. So this is not difficult to see. So in some sense, the two functions we consider cosine or this integral are in some sense maybe the simplest transcendental entire functions which are not the exponential function. So I have here two pictures of functions of the form, well, introduce some parameters, alpha times the integral plus beta, and it is such that you have a periodic point, attracting periodic point of period 2. And the parameters have been chosen, so the immediate attracting basin, say, of Z naught. In one case, the intersection with the escaping set, the boundary, the immediate attracting basin with the escaping set has dimension 2. In one case, it has dimension 1. Do you see from the pictures? Does anybody, well, except my co-author, see or at least has a guess? So we look at the yellow region containing Z naught. Where do you have dimension 1? Where do you have dimension 2? We can also take a vote. So who thinks we have dimension 1 in the left picture? Who thinks we have dimension 1 in the right picture? This is an excellent audience. You are all right. So, it is like this. Next question. What is, say, the difference, say, from a dynamical point of view? So what is the so why? Well, these functions there must be some difference in the dynamics. What is the difference in the dynamics?
Contains both asymptotic values.
Yeah.
Exactly. So well, I haven't told you what the asymptotic values are, but you know what the asymptotic passes are. So, and the asymptotic passes are positive and negative real axes. And in the right picture, they are both in the basin, and in the left picture, they are in different basins. So this is the difference. So, sorry. So we come to a result first. So more generally now we consider functions of the form integral p times e to the q with polynomials p and q. Such functions are in the Schweizer class, and the result is, or the first version of our result is, that if you have a function of this form integral p times e to the q, which has an attracting periodic point of period greater than 1, suppose that the singularities of the inverse are all in one attracting basin, then the dimension of the boundary of this immediate attracting basin intersected with the escaping set has dimension 1. And there is an example. This was the example in the left picture on the previous slide. So there is an example where this dimension is 2, and well, this is here the function minus 2 times this integral. So, so this just means the hypothesis is necessary somehow. So if the singularities are not all in the same immediate attracting basin, then the dimension may not be one, and there may actually be two.
I understand, sorry.
Yeah.
I understand that you mean in the same component of the immediate
The
basin.
same component of the immediate basin.
But one in each.
Yes. So in the sort of example, there we have an attracting cycle of period 2, and so each of these two components contains one singularity of the inverse. So yeah, and I mean, of course, for where there is a general result that if you have an attracting periodic point, then the immediate attracting basin always contains at least one singularity of the inverse. For the exponential functions, there is only one singularity of the inverse, so then it automatically contains all of them. So, well, we do not know whether this holds perhaps for all functions in S, but we will see that it holds for some more general functions. And for example, the pictures you saw at the very beginning were or for functions of the form alpha cosine z plus beta. For such functions, it also holds, and for some more general functions. So for the more general version, so we consider the so-called logarithmic change of variables. So this is a tool introduced by Yeremenko and Ljubich. So, and to study the class S, actually they studied a more general class also, the so-called, well, nowadays called Yeremenko-Ljubich class. This is a class where the set of singularities of the inverse is bounded, not only finite, or not finite, but just bounded. Well, what we do could also be extended to with some additional conditions to this class, but maybe I will not talk about this. So you choose a large number R bigger than f of 0, such that the singularities are contained in the disk of radius R. So this is a disk of radius R, and it contains f of 0 and all the singularities of the inverse. You take the pre-image of f, so this is some domain not contained. Well, it could be several domains. So for simplicity, I've drawn only one. So, and then you take the pre-image of this under the exponential function. And what they show is, well, then there, this little function little f can be lifted to a function capital F. And this function capital F is univalent in any component of its domain of definition. So, and what they prove is, well, and this is once you know that you have this function capital F, which is univalent in any of these components here, once you know this, it is a fairly simple consequence of the Köber 1/4 theorem that then mod f prime is bigger than 1/4 times real part of f of z. Well, there is this log r, but actually you could always normalize things so that that r is 1, so that this is gone. So the essential thing is that mod f prime is bigger than the real part of f. And the hypothesis that we will make or will have to make is that mod f prime is not only bigger than the real part of f, but it is bigger than some constant times the modulus. So this is, yeah, this, sorry, this is the hypothesis that will appear in our result. The second hypothesis we have to make is that the function has finite order. This is also a definition which appeared in previous talks already. So function, entire function f is said to have finite order if mod f of z is less than the exponential to some power of mod z, and say for large z. And the infimum of the exponents you can take here, this is called the order. So The theorem now says the following. Suppose you have a function of finite order, and suppose the logarithmic transform, capital F, so the function from the logarithmic change of variables satisfies this condition we had. And then same conclusion as before. If you have a periodic point of period greater than 1, and the immediate attracting basin contains all the singularities of the inverse, then the dimension of escaping set intersected with boundary of that immediate basin is equal to 1. Just for completeness, what happens if the period is equal to 1? Well, so then you have an attracting fixed point, and the set of singularities of the inverse is contained in the immediate basin of this fixed point. Such functions are called functions of disjoint type, and well, and again you see same result as for exponential functions, that then the Fatou set is connected and consists only of this immediate attracting basin. Its boundary is a Julia set, and the result of McMullen about the dimension also extends to the setting. This is a result of Czesław Baranski and Hendrik Schubert. So that if you have a function f, well, actually their result is also holds for the Yeremenko-Lubitsch class as well. So if a function in this class has finite order, then Julia set and escaping set have dimension 2. Well, I told you for if you do something like alpha cosine plus beta, so you have the same result. So there are also some pictures which are of no relevance for the talk, but I thought after barbecue, and so it is maybe good to have a few seconds of relaxing. Okay. So well, here Z0 is mapped to Z1 and second also 1 to Z2. So, but now let me say at least sketch some ideas of the proof. So first, and this was actually done in the pictures already. So well, instead of assuming that the singularities are in A of Z0, A star of Z0, you can also assume that they are in A star of Zj for any other j. So here Zj is always Fj of Z0. So the periodic cycle is Z0, Z1, Z2 up to Zp minus 1. Well, this you could just renumber. But and also, well, if the dimension of the boundary of A star of Z0 is 1, this is the same as saying that the boundary of A star of Z1 or Zj is 1. So, I mean, these boundaries are mapped onto each other by the function f, and this does not change dimension. Actually, once you have that the boundary that I have intersected with the boundary of A star of Z0 as dimension 1, you know that this is true with A star of Z0 replaced by any component of the Fatou set. So actually, we will number our singularities, our periodic points, so that the singularities are in A star of Z1. We make some, you will see a picture in a second. We make, without loss of generality, you can assume that 0 is in the immediate attracting basin of Z0, but 0 is different from Z0. This you can just achieve by linear change of variables. You can also assume that Z1, well, which is the attracting periodic point, that this is not a singularity of the inverse. So this we do by a small quasi-conformal perturbation of the function f. So this you can also assume. And well, what we do now, and well, in a second you will see a picture, we choose a Jordan curve which contains the singularities. So Jordan curve in A star of Z1, which contains the singularities and contains the point f of 0, but does not contain the point Z1. Well, and finally we connect this to 0. So the picture is the following. So here is the point Z1, the attracting periodic point Z1. Its immediate basin contains the point F0, and it contains the singularities of the inverse, which I have not drawn. But now we take a curve gamma, which contains all the singularities of the inverse and contains the point F0, but does not contain the point Z1. And also for this logarithmic change of variables, we want to take pre-images under the exponential function. So somehow we connect this also to a point, to this curve to 0. So then we take the pre-image of this. So, and because all the singularities are here, the pre-image consists of certain domains which are, well, forget this gamma naught for a moment. So these domains are mapped, well, as a covering onto the blue region here. So the blue domains here are mapped there. And, well, this curve gamma naught now has pre-images which are sort of certain spikes here. Well, and now we take the pre-image under the exponential function. And again, then you find that there is a map capital F, which maps each of these blue regions here to the blue region here. And so the reason of the spikes is here to have a simply connected region here. Well, and so, yeah. Well, what we do next now is we choose a curve, sigma here, which connects 0 to infinity. So this is this curve sigma. And also we take pre-images. We take pre-images of this curve sigma under the exponential map. So these are here, well, with distance 2 pi. There are infinitely many, or you take one pre-image and shift it by multiples of 2 pi I. So this is a picture you have, and we will then mainly study this function capital F. Well, perhaps why do we do it like this? So Yeremenko and Lyubich studied when they did the logarithmic change of variables, well, they just considered the outside of a big disk. And there, but we have to be a bit more careful. Well, somehow our periodic points that we have here, we also want to find them upstairs. So somehow we want to, from our periodic cycle for little f, we want to produce a periodic cycle for capital F. So this is why we have to be a bit careful and somehow make sure that our periodic points are still somehow in the blue regions here, where everything is defined. We also somehow want to define something like attracting basin and Julia set, and so for the function capital F. So this is also, we have to make sure that the Julia set is in the blue region here where everything is defined. But there are some technicalities somehow. Well, 0 is in the immediate basin of Z0. F of 0 is in the immediate basin of Z1. So this curve gamma naught will intersect the Julia set. So these curves and also the little curves here will intersect the Julia set. So you have to be a bit careful how you define this, but it can be done. Another theorem to be mentioned is the so-called Donjoy-Kaleman-Alfors theorem. It says if your function has finite order, then there are only finitely many of these domains. So this is known as Donjoy-Kaleman-Alfors theorem. And well, finally, maybe these domains here have a name. They are called tracts. So there are only finitely many tracts. And of course, then here in every of these strips, so this between two curves sigma j, there is some sort of strip-like domain. It also contains only finitely many. We will also call those strips, and also those domains tracts. So we will now only consider this logarithmic change, this function capital F, essentially. So this attracting cycle, z naught to the p minus 1, corresponds to some attracting cycle there. So, well, and of course, the attracting cycle projects down, for capital F, projects down to the attracting cycle for little f under the exponential map. Well, so this is what I said somehow. We made sure that none of these points Zj is in the interior of this gamma. So these points Zj are really in the set we had drawn blue. So these capital points, these points Wj are also in this blue domains. So we can define some attracting basins for these capital J with these attracting basins for the Wj with respect to the capital. So, and also remember the interior of the curve gamma, or put it differently, everything which is wide was in the immediate basins. So here, everything which is wide will be in the immediate basins for the function capital F. Well, to be more precise, you have to define the attracting basin. I mean, once you are in the wide region, function is not defined. Once you are in the wide region here to the left, the function is not defined anymore. The function capital F is only defined in the blue regions. But if you define it in such a way that you say, well, it is attracting by W naught, if the iterates converge to W naught, or if it ends up in the wide region, then it is a reasonable definition of the attracting basin. So what we see is everything is what is wide is in the immediate attracting basin of W naught. But this means the other immediate attracting basins have to be in one of these strips, or more precisely, even in one of these blue domains. So, and yeah, this is what we then use. So let Sk be the strip between two such curves, sigma k and sigma k plus 1. So we see the, except for W naught, for the other Wj, so Wjj different from 0, this immediate attracting basin has to be in some strip. So, well, now, if we have a point in the Julia set, well, we look at the forward images, it will, again, it has to be in some strip. So this, and we can define a sequence, Ik, that we simply say, Ik is the number such that Fk of W is in the strip Sik. So for every point W in the Julia set, this gives you some sequence. So which is called the itinerary in particular, say if you have a point which say is in the immediate attracting basin of W1 or in the boundary of that. So if you iterate it p times, it will again be on the boundary, so it will be in the same strip. So in other words, it means this so-called itinerary is of a special form. So, and this is somehow, well, essentially the argument that Kirchhoff, Boguta, and Anna also make in their paper, that they say, if for the exponential function, you can also define these itineraries, and then the points which are in the immediate attracting basin, they have to have certain special itineraries somehow. And in some sense, you could argue there are not that many points which have these special kind of itinerary. Well, you can do this more generally, but maybe I want to do this. So what we want to do, and let's restrict to p equal to 2. I want to at least try to explain where our extra hypothesis come in. We do the following. We start with a point in the boundary of A1, a star of W1, and consider its pre-image. So here we have all these strips. Now take a point W, which is in the boundary of a star of oh, this should be W1 here. So we are only considering this capital F now. So a star of W1. So this is in, you know, in some strip. Let us suppose it is here. So this is the point W. So we look at the pre-images. So there is a pre-image in each of these blue domains. So well, I've drawn them here as green points. So what are these pre-images? Well, you only have, say, let's take the strip as naught. Here we have one here, we have one here, and then the others are shifted by multiples of 2 pi I. So the images of the red points, which are the green points, they have the form Vj plus 2 pi I k. The k is in Z, and the J runs through the number of tracts you have. So here there are 2 tracts, but by this Bourgeois-Kahneman-Alfors theorem, this is a finite number. Well, now we go one step further, take the next 3 images, but we take those which are again in the boundary of a star of W1. So these are the yellow points here. So for each green one, there is a pre-image here. So, well, so one for each, and we denote this by UJK. So the green, the yellow points are mapped to some green point and then back to the red. Well, one thing to observe is if we start, we are interested in points which are going to infinity. So we may consider points W, which are very large. So where the real part is very large. Well, I should have said this perhaps. If in the original plane, if a point tends to point Z tends to infinity under little f, then the corresponding point for the corresponding point W, the real part of the iterates will tend to infinity. So we may assume that everything is far to the right. And now, this is at least what I would want to try to explain. We want to estimate, and we want to use this estimate. And we want to use it to estimate the second derivative. Well, and let us write down what is the second derivative at these yellow points UJK. By chain rule, this is a derivative at the green point times the derivative at the corresponding yellow point. Now these derivatives we can estimate by eta times the function. So we have an eta squared, then there is a function. Well, f maps vj plus 2 pi I k to w, this ujk to, so we have this. Now, we say we start with a w, which is large. So if we are far enough to the right, this will be at least 1. This vj will also have a large real part. So the modulus here can be estimated by something like c squared plus k squared with some large constant k. So c can be taken large. And now, well, you can also do the same argument for larger values of p. So what does it mean? We look at the, well, we have a point w, and we look at the pre-images under, well, in the previous slide, it was a second iterate, but more generally, it was the piece iterate. We look at the pre-image, which are again in this boundary. 1 over these to the power t. Well, we have estimated this derivative. So this was, you have this c squared plus k squared 1/2 if you take to the power t. Well, and you have to do this, so to say, for each tract separately. So there is a multiply by number n. But anyway, you see, given a t, you can choose, well, first the series converges, and given a t, you can choose everything large enough so that the series is less than 1. So, and well, essentially, what does it mean? If you take a small radius of, a small disk of radius r around the point w, well, then the pre-images of these disks will consist of smaller disks, or is contained in smaller disks. Their radii to the power t is less than the original radius to the power t. So this, and I think this is a fairly standard then to deduce from this that the dimension of the points which are always bigger than that the points which are always bigger than some large number, that the dimension of this is less than t. And where there are some details which I will omit. So, and if you take the limit, then we really get the dimension is less than 1. And where that the dimension is at least 1, so the dimension is less than 1, that the dimension is at least 1 is also, well, this immediate basin, the boundary contains certain curves called hairs, and well, so you get dimension equal to. Okay, so this leaves me 2 minutes for the example. And so, well, yeah, the first thing let me do very quickly. So our example was this function f alpha, where alpha is -2. But there is a lot of symmetry here. And after, sorry, with a little computation, you see that the function f2 as a fixed point and the basin of attraction for this periodic point z naught for f -2 is the basin of attraction for the fixed point of f2. And to study this, the boundary of this basin, we use some results of Morozava. So he studied these functions in more detail, but essentially what you can get out of his results is the following. The immediate basin of the fixed point z2 of this function f2, so this is an attracting fixed point, consists of all points which always stay in the right half plane. So It's all points which always stay in the right half. It is clear. So by symmetry regions, the imaginary axis cannot be in the attracting basin. So all points which are in the immediate attracting basin always have to stay to the right. But there is actually equality. So there is something to prove. I will not say much about this. So also this, well, we use it in the proof, but it also can use it to produce a picture. Now, an easy way, if you want to know what is the immediate attracting basin. So this is in yellow here. So the immediate attracting basin are points which are the points which always stay in the right half plane. But you can also use it to prove. And I mentioned already this results by Henrik Schubert and Krzysztof Baranski, which show in particular if D is a tract of a function in the class S, then the dimension of the points which escape in this tract is 2. So the also dimension of the points which escape to infinity in one tract, this dimension is 2. Well, now what is our function f2? Well, maybe go back. This function has 2 tracts. So one tract is sort of here, one tract is sort of here. So if you take a large disk and consider the preimage of the outside, so we have one component here, one component here, and so the points which always stay up here, they have dimension 2. What are we interested in? Well, we are interested in the points, sort of not all points which stay in the tract, but we are interested in the point which stay in one half of the tract. Or more precisely, you could say, we are not interested in points which stay in one tract, but we are interested in points which stay in 2 half tracts. So, and believe me, if you go through their work, so it is really, we have to consider the points which stay in a half tract, and it's really minimal modifications of what they do. So shows you that points which stay in a half tract also have dimension 2. So, well, so this shows that in our example, we have dimension 2. Okay, so, well, sorry for going slightly over time. Thank you very much.
Other questions, comments?
Yeah, I have one question and one naive question comment. So I don't know in the proof where you are using that you are in class S and not in class B.
Well, we are using, well, we could do it for certain functions in class B, certainly, but we are using it at the point where we say we have a curve which contains a singularity, but does not contain the periodic point Z1. So we are in the immediate basin of attraction of Z1. This contains all the singularity. And then I want to draw a curve which contains the singularities, but does not contain Z1. Of course, you could, well, you could have more general things, but at least in principle, it is conceivable, or not only conceivable, it is possible that these singularities, say, fill out some disk or circle or whatever. And
a naive comment. So when you move from period 1 to period higher than 1,
Yeah.
you lose some value. And it looks like when you are in period 1, you need to count all the preimages because they are all normal.
Yeah.
And in the other case, it's like that you are losing the ones that belong to the.
Yeah.
And this is the, let's say, the naive reason why you get less dimension.
I think so, but maybe just when Bogusa can answer this more better. But
I mean,
this is
a naive approach, but it is.
but this is somehow the way I look at it. If you want to have the Julia set, you have to look at all itineraries, and now you are looking at itineraries which at certain places have a fixed number.
Thank you.
If you just look at yeah, the symbolic.
Yeah, okay, so
sequences,
that was the,
you have this periodic orbit which goes along some
yeah.
sequence. So generally you follow this, but one time in each loop you're allowed to take any symbol. You take any symbol, then you go p minus 1 times exactly following a pattern, and then again you have. But this set has dimension.
yeah, okay, that was. Thank you.
More questions or more comments?
In your main theorem, you have this condition on f prime.
Yeah.
So, which exactly consequences does it have on the shape of the logarithmic tract? So,
This is a very good question, which I have, well, also asked myself, but to which I do not have a satisfying answer yet. So the general idea would be, if the tract is nice, then this should be satisfied. And so but if the boundary of the tract is very wiggly or whatever, then it may not be satisfied. So this is what I would also think, but I have put it this way: I don't have a clear-cut statement yet saying, okay, this means nice boundary, and this implies it.
Comments, questions? If not, let's thank the speaker again. In 5 minutes for the.
As always, I would like to say something. So normally we should leave the rooms before 11, but we don't have to. You have to leave the rooms before lunch. So please. Obviously, this doesn't pertain to people staying for the next day.